Hello, everybody. It's time to do a little crash course on collisions. Our goal today should be to learn the four major types of collisions and be able to apply conservation of momentum to be able to solve problems involving those collisions. So to start out, we got to work with our kind of default collision, and that is the inelastic collision. There's no real characteristics to a general inelastic collision. Usually, if we don't have other clues about what else is going on, we need to assume that it is inelastic. So this is kind of our default. When in doubt, we assume something is an inelastic collision. Uh, we can say that momentum is conserved, but momentum is conserved in all collisions. But energy is not. So momentum is conserved. When we're setting up an inelastic collision, the entire idea is that the total momentum before of whatever objects we have crashing needs to be equal to the total momentum after. Each object might change its speed or, goodness forbid, mass in the process of the collision, but the total momentum should remain constant. It's a matter for us to figure out where that momentum was transferred between the objects. If we have two objects, then each object before the collision is going to have its own momentum. So we can expand this out as object 1's momentum, m1 v1, plus object 2's momentum. So they each come in doing their own thing. Afterwards, they crash. Boom! We put an equal sign to represent now we're going to look at the momentum after the collision. And mass 1 is now doing something different. We mentioned that it has a final speed. This final speed is generally going to be different than the initial speed that it came in at. And then the same thing we can write for object 2. So this equation looks like a lot. There's four different terms here, but all we're really doing is bookkeeping which objects have momentum and how much. Object 1, object 2 before the crash, object 1, object 2 after the crash. Just write it all down, and then we work with the equation that we've built. It's important to note that unlike energy, when we did conservation of energy, it didn't matter which way the objects were going. Since momentum is a vector, all these V's should have little vector hats on them, direction matters. So objects going to the left should have the negative momentum of objects going to the right. We need to take that direction into account. Left is negative of right, up is negative of down, whatever opposites you have, we need to treat them that way. So when you're thinking about your objects before and after the collision, we need to think about which way we go. That's going to affect how we mathematically treat each of these velocities along the way. So this is our baseline equation. This is, again, momentum's conserved in an inelastic collision, but it's conserved for all collisions. So we're going to start from this baseline. We're going to show that all of the other collisions equations are just little tweaks off this base formula. So if you don't memorize all of them, that's fine. You can always just memorize this one and see what falls out of it. So let's see how we can actually use this equation to analyze how things should behave in a collision. We can have the following situation. An 800 kilogram truck moves right at 4 meters per second. It collides head on with a 400 kilogram car at 6 meters per second. After the collision, the car is observed to move to the right at 3 meters per second. Our question is, how fast is the truck? after the collision. So we have 3 out of the 4 velocities here. That's the idea. We're going to be missing one piece of information out of the 4. We can use the 3 that we have to solve for that remaining piece of the puzzle. So the 800 kilogram truck's going to the right at 4 meters per second. It collides head on with a 400 kilogram car at 6 meters per second. Head on is a hint here. If the cars are colliding head on, they're coming in from different directions, and thus they have opposite velocities initially. After the collision, the car gets knocked backwards to the right at 3 meters per second. We want to figure out what the truck is doing for that to happen. So we're going to use our conservation equation. We're just going to kind of fill in all the pieces we know. We have an 800 kilogram truck at 4 meters per second. We're going to add the 400 kilogram car moving at 6 meters per second. But because it's a head-on collision, the car needs to be moving opposite to the truck. So we don't put 6, we put -6. And we've filled in all the information for the before side of our equation. Now we're going to write our equal sign and do the same thing for what we can for the after side. Our 800 kilogram truck, we're trying to find its final velocity. So we leave V1 final as a variable, and we're going to add to that 400 times 3. It says we're going to the right, so we leave it as a positive value. Now you can certainly plug this into your calculator. If you want to clean it up a little bit, you can note that each of these terms basically is multiplied by 400 to some extent. So we can divide through by 400 to kind of clean things up. 800 by 400 gives us 2. 2 times 4 is 8 plus -6 equals 2v final plus 3. So that's much cleaner than before. We can clean that up and get 2 equals 2v final plus 3, or move the 3 to the other side, we get -1 equals 2v final, or v final equals -1/2 meters per second. So that's our final answer. There's a lot of information here. First of all, we have the fact that the car is, what its speed is at the end of the day, but also this sign is very important here. The fact that we got a negative sign as our answer means it needs to be traveling in the negative direction. So this tells us, just like the car was initially going to the left, moved to the right after the collision, the truck bounces off as well and goes to the left afterward. So this minus sign informs us that the truck goes leftward after the collision. So it's always important to keep your sign straight. We don't need to know that the truck bounces off initially. The solution tells us that based off whether our final answer is positive or negative. It's a good system. If you keep track of what you do know, left and right, your final answer should come out to be whatever it needs to be based off just that sign. So that's an example of an inelastic collision problem. Inelastic collisions have energy not conserved. If we want energy to be conserved, we have to look at elastic collisions. This is a collision where both energy and momentum are conserved. I like to think that elastic collisions conserve energy. The one that conserves energy also starts with an E. So that's pretty nice. We can remember that. Really, since momentum is conserved, we still get our classic momentum conservation equation. It's exactly the same as in an inelastic collision. It's just that now we get a second piece of information. If energy is conserved, then the kinetic energy of our system will not be lost, and thus we can say 1/2 mv1 squared plus 1/2 m2v2 squared. In other words, the kinetic energy of car 1 plus the kinetic energy of object 2 before the collision need to equal whatever the kinetic energies are doing after the collision. I switched places. M2 came first, M1 comes second. Doesn't really matter. But the idea is these are final velocities. So these velocities after the collision generally are not going to be the same as they were before. So we just designate them as finals. So the beauty of an elastic collision is we have two equations and two unknowns. We have two equations which lets us solve for two unknowns. In the inelastic case, we need to have three pieces of information to solve for the fourth. For an elastic collision, if I know that it's elastic, if I'm told the initial velocity of object 1 is this and if the initial velocity of object 2 is that, I'm able to use these two equations together to solve for both of the final velocities, for example. It gives you the ability to solve for what's going on in the collision without more information, which is useful. It turns out that, solving these two equations together actually ends up being kind of beastly. It's a difficult, algebraic task to do that. And so I will relieve you by saying you will probably never have to solve an elastic collision using both energy and momentum at the same time on a test. It's just a lot. It's too much math to make it a good test question. You definitely need to know that an elastic collision conserves energy. What you should be able to do is, if you have all four velocities, you should be able to confirm whether or not a collision is elastic or not. So if I use this energy equation, if I have my masses and my velocities, I kind of just plug and chug. I can compare total KE before to total KE after. If they match, if they're equal, then it's elastic. If it's not, then it is inelastic. Else inelastic. There are tons and tons of AP style problems where they have students, analyzing a collision, they're collecting data, and it'll say something like, how could the students figure out what kind of collision they observed? Well, you're going to want to do something like measure masses and velocities before and after. And then compare kinetic energies before and after. So if you were doing an experiment to verify how elastic a collision was or whether something was elastic or inelastic, you would find a way to measure the velocities before and after. You would use that to calculate kinetic energy. And then, if it's the same, you have an elastic collision. If not, you have a kind of a boring old default inelastic collision. So that's what we need to know for elastic. Energy is conserved. We're able to compare kinetic energies before and after. Moving on. There's also something called a perfectly inelastic collision. The main characteristic of this sort of collision is that the objects will stick together, or they'll move as a unit after the collision. So your examples of this, physics textbooks love, like you throw a blob of sticky clay at like a wooden block on a table, and then they glom together and they move together as a single object. You had two objects that were apart, and now you have one object that's together after they collide. You could do this also with like a dart or a bullet. If the bullet gets embedded into the block, they might move together after the fact. You could have train cars coupling together. When they crash into each other, they lock together and they glide down the tracks as a single, vehicle together. It could even be something like you have figure skaters on ice. They skate towards each other. The guy picks up the girl and they move to one side as they're doing that routine with each other. So you had two people that were apart. They come together somehow and they move together after they interact somehow. So it could be like skaters doing a lift. Anything where you have two objects coming together after the collision. Momentum is conserved, energy is not. So that's your typical collision thing. We get to use momentum. So we set up our momentum equation. M1 V1 plus M2 V2. Before the collision, each object's doing their own thing. After the collision, they stick together. So if they're moving together, there's really only one final speed to track. So we write V final over there. That object, if they're together, should have a mass equal to the sum of the two masses there. So this is M1 plus M2 times that final speed. Really what we've done is we've taken our baseline, this could be M1 V1 final plus M2 V2 final. If they're moving together, we know that V1 final is equal to V2 final, and we can kind of factor that out to the right as the same values. We just kind of factor it out. If we were to distribute it back in, we'd get our baseline equation. So this is a little shortcut. You take some shared final speed and you multiply it by the sum of the two masses. So this is kind of a combined mass. This is a shared final speed. So we can do a quick example of a perfectly inelastic collision. Let's say we have an 80 kilogram skater moves right at 4 meters per second, and a 60 kilogram skater skates left at 1 meter per second. They collide, quote unquote, hopefully not injury. We're using that just to mean they interact with each other and skate together afterwards. What is the final speed? So we set it up like usual. We have skater 1 has 80 kilograms of mass. It's going at 4 meters per second. Skater 2 has 60 kilograms of mass and is moving at 1 meter per second to the left, -1. That equals the combined mass. 80 plus 60 gets us 140, and they're moving at some final speed. We can divide through by, 10. We get 8 times 4 is 32. Plus minus 6 equals 14 V final. That gets us to 26 equals 14 V final. V final is equal to 13/7 meters per second. You can simplify that in your calculator if you want. Thing to note here, the answer is positive. So that means that both of them are traveling together in the same direction as the 80 kilogram skater that we designated as moving in the positive direction. And that makes sense. The 80 kilogram skater has both more mass and more speed, so his overall momentum is definitely dominant here. That means the final momentum, if this is to be conserved, even though the other skater was going in the other direction, when they come together, they're still going in the dominant direction of the 80 kilogram skater. So that's something to think about. Does your answer make sense? Which of my two objects had the most momentum? Should my final velocity reflect that same direction? So it's kind of a little good sanity check you can use to make sure you're on track. In addition to a perfectly inelastic collision, our final type of collision is the explosion. I like to think of it as a perfectly inelastic collision in reverse. If a perfectly inelastic collision was two objects sticking together, the explosion has, one object breaking apart into multiple objects. So one object breaks apart into multiple objects. Even in an explosion, momentum is conserved. If you have an object and it blows into 1,000,000 pieces, if you were to keep track of the masses and velocities of each of those 1,000,000 pieces, they would still have to have the same momentum as your original object. So it's not a collision in the sense that things are crashing, but there is, forces being exerted somehow, and momentum still needs to be conserved in that interaction. So your examples could include like a literal fire and gunpowder explosion. You could have like a firework would be an explosion. You could have, any two things that are together that are coming apart. If you were on really slick ice so that the friction is minimal and you threw a heavy ball, you would throw the ball one way. To push off of the ball had to push on you, and you would come apart going the other way. So, like, throwing a ball is even a kind of a weird way of thinking of an explosion. The reason you don't usually go backwards whenever you throw a ball is that friction holds you in place. But if that were gone, you would go backwards. So throwing a ball, anything where you have two things together and they eventually come apart. If you jump off a raft on the surface of a pool, you're going to go backwards. The raft is going to be pushed forwards by that thing. That's an explosion. You're still using the same base conservation of momentum equation, but for an object initially at rest, that breaks into two pieces. We can get kind of a little cheat equation that's nice to think about. Initially, I have zero momentum. If I'm at rest, I'm not moving, my velocity is zero, therefore my momentum is zero. So my before side of the equation's just a big old zero. Objects break apart. One object goes one way, m1, v1. The other object must go in the opposite direction. If I started out with zero momentum, and this object goes, say, to the right, in order to maintain or conserve the momentum I started with, I need the other object to go to the left, minus m2 v2. So I kind of preemptively put the minus sign here to indicate objects go in different directions. Now again, this is a special case. You certainly could have an object that's moving and then explodes, in which case you would just include the original object's momentum over here. M total, V initial, or something like that. But this is kind of a nice common case that occurs enough that it's worth kind of having this equation in the back of your head. You start out with absolutely no momentum, but then all of a sudden things are moving. Those things have momentum. But for momentum to be conserved, I need the object going to the right exactly to cancel out with the object going to the left. If I have a really heavy object going to the right, that means that the lighter object going to the left needs to be moving proportionally faster to make that happen. You can kind of rearrange this to get m1 v1 equals m2 v2, and therefore m1 v1 is equal to v2 over v1. If the object is heavier over here, m1, the other object, object 2, needs to be going faster to make that happen. So that's what we can expect from an explosion. Moral of the story, in all collisions, whether they're elastic, perfectly inelastic, explosion, or just regular elastic, momentum is conserved. We can use momentum conservation to solve or set up and learn information about that system. So there's a very powerful technique that lets us, predict what will happen in a collision, or, if we want something to happen, it lets us predict what we need to do at the beginning to get our end goal. All right, we're going to call it there. Have a nice day.